This is the fourth and final section of the chapter on polar coordinates, and what we're going to be doing here is finding tangents to polar curves, and the only tangents that we need to find are tangents which are either parallel to the initial line or perpendicular to the initial line. So what does that look like? So let's say, for example, here's my initial line here, initial line. And let's just put some dotted lines here to show pi over 2. And let's say I've got a graph, a polar graph that looks something like this. So you may recognize this type of shape, so something like that. And there are tangents all around this, but the only tangents we're interested in are tangents which are parallel to the initial line. So tangents either here, or here. So these two tangents are parallel to the initial line, and the way that we find those tangents is that we work out dy d theta equals 0. So dy d theta equals 0. Now, tangents which are perpendicular to the initial line are going to be, well, I can see one here, there's going to be a tangent there perpendicular, and there are tangents here and here. So these green ones here are perpendicular to the parallel line, and the way that we find those is we do dx d theta equals 0. So it's all about doing differentiation, and when we differentiate, set that equal to 0. Then from that we can work out what theta is. Okay, so once you've worked out these things here, you'll then work out what theta is, and then you can substitute theta back into the original equation. So substitute back into the original equation to get r. Okay, and your final answer is going to be the coordinates where these tangents are, which is going to be given in the form r theta. Okay, and that's basically what we need to do. So it's only tangents which are parallel and perpendicular to the initial line. Right, so we want to find the coordinates on this line here, where the tangents are parallel to the initial line. Now, if it's parallel, that means we've got dy d theta equals to 0, parallel to the initial line. So it's always going to be parallel, perpendicular to the initial line. So how am I going to get this r equals a 1 plus cos theta? How am I going to get that in the form y equals something with theta? Well, I'm going to use y equals that r sine theta. Yeah, so if I rearrange that, I will get r equals y over sine theta. I'll substitute that into here, the original equation, so I'll have y over sine theta equals a and then 1 plus cos theta. So we'll times both sides by sine, and we'll get y equals a 1 plus cos theta times by sine theta times sine theta, like this. Now what I can do from here, I can actually use the product rule. So I'm going to write it like this. So let's put the maybe the a. So we've got a plus a cos theta. Okay, and that's going to be times by sine theta. So I'm going to use the product rule, and with this product rule, I will have u equal to a plus a sine cos theta. Now remember, a is just a constant, and I will have v equal to sine theta. So u dash, let's do that here, u dash, when I differentiate that, is just going to become negative a sine theta, and phi dash, that's just going to become cos theta. So dy d theta is going to become, using the product rule, u times v dash, so that's going to be a plus a cos theta times by cos theta, and plus, it's actually going to be minus, because u dash is minus, so minus a sine theta times by sine theta. So we're going to be able to do a little bit of simplifying here. Now, because we're setting this equal to 0, it might be helpful to say, right, if I took this a outside the bracket, okay, probably not much point putting in a bracket anyway, like this, and I've got this here, write out as sine squared theta, then I can divide both sides by a. That means that a is gone. It makes it a little bit easier to deal with, and actually then I can expand the brackets. I can forget about the a, and I will have cos theta, this is expanding the brackets as well, plus cos squared theta, so the a just goes because we've cancelled that out, minus sine squared theta equals 0. Now, if I want to work out when this is equal to 0, I really want to be able to factorize it. So this is a problem, the sine squared, but I can use cos squared theta is equivalent to 1, other way around, sine squared theta is equivalent to 1 minus cos squared theta, because sine squared plus cos squared is 1, so you just take away cos squared from both sides. So what we now have is cos theta times by cos squared theta, plus cos squared theta, and then minus 1 minus cos squared theta. That's got to equal 0. So from there we will have cos theta. Now if I expand the brackets, I'm going to have a cos squared theta plus another cos squared theta, so plus 2 cos squared theta, and then minus 1. Now, does this factorize? Hopefully it does. So I'm going to have cos, or 2 cos theta here, cos theta here. Because I've got the number 1, got to have 1 and 1 there. Now, how can I get just a cos theta, 1 cos theta, and a negative 1? One of them needs to be negative. So I could say, right, I put a plus here. So I get 2 cos theta and then 1 there. Right, so that now works. So we're well on the way to working out when this is equal to 0. So it's either when this bit is 0 or when this bit is 0. So for this one, the first bit, it's going to be when 2 cos theta equals 1, or when cos theta equals a half. We'll work that in a minute. Then for the second bracket, it's when cos theta equals negative 1. So we're going to grab our calculator so that we can do some cos inverses and work out what these are. Right, so from the, if we do the cos inverse of a half, then we'll get a principal solution of our pi over 3. Okay, now remember we're going all the way around. This initial line can go all the way around to 2 pi. So, and you can use a cast diagram to help you. The next value for theta can be 5 pi over over 3. Okay, so we've got those there. And then if we do the cos inverse of negative 1, we'll get a value of theta as pi. There can't be any other positions that angle can be in. Yeah, so that's just pi there. The next value will be like 3 pi, which is exactly the same position. Is the next value 3 pi? Let's have a think. So when cos is -1, yes, it would be 3 pi. So there's our values of our angles. What we need to do now is to work out the values of r we get from that. So now we substitute those values of r into, those values of theta into the original equation, get the values of r. So if I put r equal to a, so this is going to be 1 plus cos, and cos pi over 3, and then we'll try the pi 5 over 3 and see what we get. So the bit in the bracket gives you 3 over 2, and we've got the a, so it gives you 3 over 2a. Now, if you put 5 pi over 3 in, you get the same answer, because basically it's a half, isn't it? Yeah. And then for the second one, we'll do r equals a, and then we've got 1 plus cos pi, 1 plus cos pi. Now actually we could just do, well, we know that cos theta is -1, you just do you could just do 1 plus -1, yeah, so you could do it that way. And what that gives us is a value of 0. So the coordinates of the points where we have these tangents are parallel to the initial line, they're going to be at the following coordinates. So one of the coordinates, remember we'll write it as r theta, is going to be 3 over 2a, comma, pi over 3. And then we're also going to have 3 over 2a, 5 pi over 3. Or you could have negative pi over 3. And for the other point, the value of r is going to be 0. And like its argument, its angle is pi. So here we have the 3 basically coordinates where the tangent is parallel to the initial line. So there we go. Okay, so in this example we need to find the equations of the points of contact of the tangents. So let's just go through this. So the points of contact are going to be polar coordinates like this. If we want to find the equations of these tangents, then we'll use x equals r cos theta, or y equals r sine theta, and then we could rearrange those to make r the subject. So rearrange to make r the subject. Now tangents, depending on whether they are parallel or perpendicular to the initial line, if they are parallel to the initial line, then we'll find those tangents by setting dy d theta equals 0. If they are perpendicular to the initial line, we will set dx d theta equal to 0. Here's the equation of the curve. Here we've got some limits in terms of theta, so we need to make sure that we reject any solutions. As we go through, we're probably going to be solving some simple trig equations, but we'll reject any solutions outside this range. So we need to keep that in mind as well as we go through it. And part A, if we're finding now a tangent which is parallel to the initial line, so the first thing that we do is we write that dy d theta equals 0. So we need an equation that we're going to use that's got y in it and theta. So we start by writing y equals r sine theta. Then from here, all we need to do is to substitute this r for a sine 2 theta, so we'll do that. So y equals not r, but a sine 2 theta sine theta. So we need to differentiate this, so we're going to find dy d theta before setting it equal to 0. Now to differentiate this, we're going to use the product rule, and we'll use u as a sine 2 theta and v as sine theta. So u dash, when we differentiate it, will become 2a cos 2 theta, because we are using the chain rule. So you differentiate the sine to become cos, then you'd multiply by that differentiated, which is 2. And then v dash will just be cos theta. So let's write down now what dy d theta is. So that will be u v dash, so a sine 2 theta cos theta, plus vu dash, so that will be 2a cos 2 theta sine theta. So the next step now is to set that equal to 0. So we'll have a sine 2 theta cos theta plus 2a sine cos 2 theta sine theta. So we set that equal to 0, and it's about solving this equal to 0. So we can divide both sides by a, because we're trying to find theta, aren't we? So yeah, if I divide both sides by a, then that will give us sine 2 theta cos theta plus 2 cos 2 theta sine theta equals to 0. Now this needs to be something, or turned into something that I can factorise. So I need to do something with the sine 2 theta and the cos 2 theta and turn them into expressions where it's just sine theta or cos theta. Well, using these identities, sine 2 theta is 2 sine theta cos theta, so I can sort of substitute that out for this 2 sine theta cos theta, and also cos 2 theta, that will be I can change that to 2 cos squared theta minus 1. I could use 1 minus 2 cos squared theta, or cos squared minus sine squared, but I've got a suspicion that if we did, we would probably have to make another substitute later on. Right, so the sine 2 theta will change to 2 sine theta cos theta, then times by cos theta. So I'll just underlining in green as the bit that we'd substituted from here, and then plus 2, and then it's going to be 2 lots of this, so I'll put that in brackets, 2 cos squared theta minus 1 times by sine theta equals 0. So again, I'll underline in green where I've done the substitution. Now we'll multiply out the brackets down here. So I'll have 2 sine theta cos squared theta, and then plus 4 cos squared theta minus 2, and then that gets multiplied by sine theta, so I'll actually do that as well. So I'll have a sine theta there, and then minus 2 sine theta equals 0. Now you'll notice, because we made the that substitution as the cos 2 theta equals 2 cos squared theta minus 1, these two terms are actually the same, yeah? And these bits can be simplified. You've got two lots of sine theta cos squared theta plus 4 lots of sine theta cos squared theta. So that just becomes 6 lots of sine theta cos squared theta minus 2 sine theta equals 0. And now we'll divide everything by 2 and factorise it, and I will be able to factorise out sine theta. So if I divide everything by 2, then obviously that becomes 3, that just becomes 1, and I will have sine theta outside the bracket, and in the bracket I will have 3 cos squared theta minus 1 equals 0. Now this is something that I can solve, because basically it's either sine theta equals 0 or it's 3 cos squared theta minus 1 equals 0. So solving the first equation, sine theta equals 0, well, that's going to be theta is like 0, pi, 2 pi, so on, like that. But if we go back to our range of values, theta can't be more than pi over 2, so that means we reject these solutions. So we just have the one here, which is sine theta equals 0. We'll do the same with this bottom equation here. So if we rearrange it, we'll get something like cos theta equals, so we'll have 1 over the other side, divide by 3, and it'll be plus or minus the square root of that. So then we will, doing a cos inverse of plus a third and minus a third, and we'll get 0.9, these are just the three significant figures, 0.955, that's with plus root a third and minus root a third, would give you 2.186, that's 3 decimal places. Again, we go back to the range of values. This is bigger than pi over 2, so we cross that out, we reject that, so that just gives us this value for theta. So now we have our values of theta. The next thing is we need to work out what the values of r is, because we want the point of contact before we move on to find the equation of the tangent. So point of contact is in the form r theta. So we have our theta. So when theta is 0, and that gets plugged into the equation, we're going to have r equals a sine 2 times 0, because theta is 0. So that will give us r equals 0. So that point of contact is going to be the point 0, 0. R equals 0, theta equals 0. And then when theta equals the other value, which was 0.955. Now we're going to use a little trick in a moment, because we want to get an exact value. Remember, this came from doing the cos inverse of the root 1/3. Yeah, that's where we got that value from. Now remember, it wasn't the minus root 1/3, because that gave us a value out of the range. So let's see what we can do to try and get an exact value. So r equals a sine, and it's it's going to be this 0.955 times 0, or sorry, 2 times 0.955, so 2 times 0.955. I'll put dots to say it goes on, but actually what I'm going to type in is not 0.955, but actually type in here the cos inverse, so 2 times this, so I get an exact value for R. So let's do that and see what we get for R. Now that actually gives us a decimal 0.942. Now I'm going to see if there's another way we can get an exact answer. So let's use a right angle triangle like this, call this theta, and we had here that it's cos theta. Let's write this down here. Cos theta is equal to, well, that's going to be 1 over root 3 positive. So if we use this right angle triangle, it means that the adjacent is 1, the hypotenuse is root 3, which means this side here is root 2. So here we can get an exact value for sine theta. So sine theta, its exact value would be root 2 over root 3, or root 2/3. So we can now use a trig identity to get the exact value of sine 2 theta, and we're going to use this one here. Yeah, so sine 2 theta, which is basically what I need to work out here, is going to be, so sine 2 theta, that will equal 2 sine theta cos theta. So 2 sine theta, which is this, times by cos theta, which is this. Now what does that give us for sine 2 theta? 2 root 2 over 3. So now let's go back and let's take that out and see if we can now get an exact answer. So the way that we work out R, so R is A times sine 2 theta. Now we've just worked out sine 2 theta is 2 root 2 over 3. So what we'll get is R equals 2 root 2 over 3 A. So now we've got the value of R for this point of contact. So finishing off this part, we haven't got to the equation yet, but the points of contact in the form R theta are 2 root 2 over 3 A 0. Okay, so that was from using this value of R and this value of theta, and then the other point of contact is going to be 2 root 2 over 3 A. Just realised I've done a 0 as a theta, that should be a 0. Did it again. 0. And then the other one is 0.955. So that came from using this value of R and this value of theta. So let's just highlight those before we carry on with the rest of the question. Right, so I've got here all the bits that we had before that are going to be useful, including the right angle triangle we got when we did we had to do the cos inverse of 1 over root 3, or as root a third, and that gave us this theta equals 0.955. But I might use that triangle in a minute to get some exact values. Now, if I look at the first bit here, and I want to work out what the equation of this tangent is. Now remember, all of these tangents are parallel to the initial line. So if I was to draw like a little sketch like this, so here's my initial line here. So these tangents are basically, they're going to be somewhere that's parallel to them. Okay, now the first one has a value of theta as 0. So if theta is 0, it means this is the tangent here, yeah, because it's contacting the contacting that point that I've got here at this point. R equals this, theta equals 0. That means that the equation of the tangent that has this point of contact is basically the initial line, so I'll write that down. So the equation of the tangent in contact, not is, in contact with the point 2 root 2 over 3a comma 0 is the initial line. So actually there's no working to do on that because of the actual angle that we have. And if that angle is 0, it basically means that the point of contact is like somewhere along here, and that distance there is 2 root 2 over 3a. So we need to do the second one, which is the other point of contact, which is this one here. So we want to find the equation of that tangent. So maybe if I was to sort of sketch what that might look like, so it's some sort of tangent up here where the point of contact is like this, and what we have is that we have a distance r that's 2 root 2 a over 3, and this angle here is 0.955, just to give you some sort of idea what it looks like. Those two crosses actually wouldn't be in exactly the same place. That X would be a little bit closer like this. Yeah, so we've got some sort of idea of the line that we're trying to find the equation of, this line here. Right, so let's just clear this out of the way because we don't need that. Now when we write the equation of any line in polar form, we want it in the form r equals something. So we'll start with y equals r sine theta. So from there we'll have r equals y over sine theta. We can tidy it up a bit and say that r equals y cosec theta. So our job now is to work out, well, what is y? Now we can do that because we know that y equals r sine theta. So we just substitute in the other point of contact. The other point of contact is the 2 root 2 over 3a, and then this 0.955. Now this 0.955 came from this, doing cos theta of 1 over root 3. Now from that I can say, well, that sine theta, the sine of that angle, using the triangle that I've got here, is going to be root 2 over root 3, opposite over hypotenuse. So root 2 over root 3, or you could just say root 2/3. So when we come to substituting sine theta, we'll use this root 2/3 as the exact value. Right, so y equals r. So r is 2 root 2a over 3 times by sine theta. Now sine theta is root 2/3. So we don't need to do sine of this. We want the exact value. So that will give us y equals, so I'll just multiply that out, 4 root 3 over 9a. Then that value of that value of y we can substitute in here to give us the final equation as y equals 4, also r equals 4 root 3 over 9a cosec theta. So there we go, we've now got both of these equations from these points of contact. One was the initial line, because the value of theta was 0, and the other was this one. So now we're ready to move on to part B. So on to part B, we are finding the equations and the points of contact like before, but now it's perpendicular to the initial line, which means that dx d theta equals 0. So our equation is r equals a sine 2 theta, and we know that x equals r cos theta, so we can substitute the r for a sine 2 theta to get an equation with just x and theta in it. So we end up with x equals a sine 2 theta cos theta. And now we want to find the x d theta. Before we set it equal to 0, so we're going to use the product rule to differentiate that. So u will be my a sine 2 theta, and my v will be cos theta. So du d theta, or u dash, is going to be 2a cos 2 theta. My v dash will be negative sine theta. So dx d theta is going to be u v dash, so that's going to be negative a sine 2 theta sine theta, and then plus vu dash, so that will be 2a cos 2 theta cos theta. Now we need to change the sine 2 theta and the cos 2 theta. Now the sine 2 theta, we have no choice. Sine 2 theta, the only identity we've got is the 2 sine theta cos theta. However, with the cos 2 theta, we have 3 choices: 2 cos squared theta minus 1, or 1 minus 2 sine squared theta, or cos squared theta minus sine squared theta. So which one do we choose? Well, let's try and think ahead. When When this part gets multiplied out, we will end up, when I make this substitution, I'll have sine cos times by sine. I'll end up with sine squared times by cos when it gets multiplied out. I really want to get the same here, sine squared times by cos. Now how am I going to get sine squared in here? By replacing the cos 2 theta with this second identity here. So this is the one I'm going to choose to substitute, because I want like that sine squared cos in both terms. So let's do that. Let's now do the substitution. So dx d theta will be negative a times by 2 sine theta cos theta times by sine squared theta. So there's the substitution, plus 2a, and I've decided I'm going to change the cos 2 theta to 1 minus 2 sine squared theta times by cos theta. That can be multiplied out, and that will give me, if I multiply everything by negative a sine theta, so I'll get negative 2a sine squared theta cos theta. So there's the sine squared cos. I'm going to get, I want the second thing in, the same thing in the second one. So if I multiply the terms by 2a cos theta, then I will have 2a cos theta and then minus 4a sine squared theta cos theta. So you notice now this is what we wanted. I've got terms here which can go together. They are both sine squared cos theta. So simplifying, I will have dx d theta equals, let's swap them around, 2a cos theta minus 6 a sine squared theta cos theta. Right, we want to make this equal to 0. So dx d theta equals 0 will be the next step. So if I make it equal to 0, I will have, and yeah, I'll write it all out, 2a cos theta minus 6a sine squared theta cos theta equals 0. We'll divide everything by 2a, so that will just leave 3 there, and we'll factorise it as well, and cos theta will be the common factor, so that will mean in brackets I will have 1 minus 3 sine squared theta equals 0. So we'll now solve this. So if we solve the cos theta equals 0 and we do the cos inverse of 0, we'll get pi over 2 equals pi over 2. So we've got 1 point of contact. Then we want to solve the other bit. So 1 minus 3 sine squared theta equals 0, which basically means that sine theta is going to be, let's have a look, we'll move the 1 over, yeah, we'll have plus or minus root a third. This will give us theta is either, to 3 significant figures, plus or minus 0.0615, 3 significant figures. The negative one is out of the range, so we ignore the negative answer for theta. So we've now got our values of theta for the points of contact. We want to use that to work out the values of r. So that's going to be the next bit. So let's make a bit of space up here. So let's start with the first bit. when theta equals pi over 2, substituting that into the equation, r equals a sine pi over 2. So we get r equals to 1. Now, like the previous one, where it was the actual initial line was the tangent, here we've got a tangent with an angle of pi over 2 going up to 1 basically, or it contacts at this point 1. So it's a line that goes up like this, contacting at this point here where the value of r is 1. So rather than write an equation, we can actually say that the equation of this tangent of that point of contact is actually the y-axis. So I'll write that down. So the equation of the tangent with, I'll just write POC, point of contact of 1 pi over 2. So there's our point of contact. The equation of that tangent is the y-axis. Yeah, so you can imagine that we've got our initial line here, we've got our y-axis there, basically where the angle is pi over 2, and that is where the tangent is. And at a point which is 1 unit above the pole here is where our polar graph is in contact with the tangent. Okay, so that's like a unit of 1 up there where it's in contact. So now moving on to the second point of contact, we'll need to create a bit of space up here. We'll write down what that point of contact is, and we're going to work out what the equation of the tangent in that point of contact is. So a bit of space, and then we'll carry on. Yep, so this second point of contact, where we've worked out theta is this 0.615. Now remember, we got that from doing the sine inverse. It was actually plus root a third. So we can use that to get the exact value for cos theta if we need it, which I think we'll need in a moment. So the opposite, 1, the hypotenuse root 3, that gives the adjacent as root 2. Now we want to find the value of r from this value of theta. So we go back to the equation. R equals a sine 2 theta. Now what we can use is the double angle for sine. So we'll have r equals a, or 2a, because we're going to replace the sine 2 theta with 2 sine theta cos theta. That allows us to find the exact value. So r equals 2a times by, now what was sine theta? Root a third. And what was cos theta? Well, we can get cos theta from this diagram down here. Cos theta, it's going to be the adjacent over the hypotenuse, so basically root 2/3, or root 2 over root 3. So plugging that into here, we'll get an exact value for r, and that gives 2 root 2 over 3a. So before we go any further, let's write down what this point of contact is, so we can see it clearly. So that point of contact was 2 root 2 over 3a, comma 0.615. So remember, that's rounded. So the next thing we want to do is to work out the equation, just like we did before. Now, just like before, we need the equation in the form r equals something. So if we start with x equals r cos theta, if we rearrange it to make r the subject, we'll have x over cos theta, and that can be changed to r equals x sec theta. And that's what we're going to use to write the equation. So we now need to work out what x is. So creating a bit of space down here. So we know that x equals r cos theta. Now we know r and theta from the point of contact. So r is 2√2 over 3a, and that needs to be times by cos theta. Now I've rubbed it out, but we did have the exact value of cos theta, which was √2/3. So we'll use that to find the exact value of x, which is 4√3 over 9a. So now the last bit, now we can write down the equation in this form, r equals x sec theta. So that will be r equals 4√3 over 9a sec theta. So this now is the equation of that tangent with this point of contact. So it's quite a long question, quite a lot to do, but I've gone through it slowly so that you can understand exactly what's going on. Obviously in the exam you would go through this much quicker. You would know your trig identities to make substitutions much more quickly than I've done it, but I've tried to give you a few little tips as we've gone along. But if you've got some sort of idea of what this tangent looks like, because basically it's going to be a line that is horizontal or vertical, if you know that that line either goes through or has an angle of 0 or goes through the origin, you know it's basically going to be the initial line, or it's going to be on the y-axis. That will save you time rather than working out the equation. If you see the angle is 0, then it's going to be the initial line, is going to be the tangent. If it's got an angle of pi over 2 or even negative pi over 2, it's going to be the y-axis. Okay, so we have this curve here, and we want to show that it's convex for those values and has a dimple for those values. So first of all, we need to understand what that means. So first of all, let's draw a convex curve. So you'll notice a convex curve always sticks out. If I look at the tangents at any point, those tangents will always be outside of the circle. And if I look at the tangents which are perpendicular to the initial line, those tangents, well, there's only going to be 2 of them. Okay, so let's write down a few things. So the first thing is, if it's convex, then it basically, the graph sticks out. It doesn't stick in. It also means that there's no tangents inside. The tangents don't go inside the circle, so the tangents are outside. Okay, so this is what convex means. And if the tangent's always outside, like this, wherever you draw the tangents, when we look at dx d theta equals 0, there's only going to be 2 of those, yeah, on either side of the curve. So if it's convex, the graph always sticks out, the tangent's always on the outside, and dx d theta equals 0 means that there's actually 2 tangents, one here and one here. Yeah. Right, now what if the graph has a dimple? Let's draw one with a dimple, like this. So if it has a dimple, we're going to do the same thing again, and we'll look at these dx d theta equals 0. So there's one here, one here, one here, but there's one inside. So what can we say when the graph has a dimple? Okay, you're going to get a tangent inside the circle, or the shape, tangent inside. Okay, the shape sticks in. Okay, sticks in, that's the dimple, the bit that sticks in. And when we look at the dx d theta tangents at 0, we see that there's more than 2. There's actually 4 of them. Yeah. So I'll label them. You'll see there's 4 tangents when there's a dimple. So we got 1, 2, 3, 4. So this is about proving how many tangents there are. Right, so let's solve this. So we have r equals p plus q cos theta. Now, because I want x, I can get r cos theta. I can replace with x. I'm going to times everything by cos theta. So I get r cos theta equals p cos theta plus q cos squared theta, like that. The r cos theta I can replace with x. So I'll have x equals p cos theta plus q cos squared theta. Now I can differentiate it and get dx d theta. So dx d theta, so the p cos theta will become negative p sine theta. And using the chain rule to differentiate the q cos squared theta, I will get negative 2q sine theta cos theta. I want to work out when this is equal to 0, so it makes sense to factorize it. So I can take negative sine theta outside the bracket and put p plus 2q cos theta inside the bracket equals 0. So let's solve this. So here I will get negative sine theta equals 0, which means sine theta equals 0, which means theta is either 0 or pi. And you can see that by if we drew the graph of sine, you can see solution here 0, pi and 2 pi, but that's going to be the same as 0 because it's back to the initial line again. And if we look at this and we attempt to solve this, what we'll have is p plus 2q cos theta equals 0, which means that cos theta equals negative p over 2q. So let's solve this. So let's use a graph of cos to help us. So here's a graph of cos. Right, so let's look at the 3 different values we could have for p and q. We could have p greater than 2q. Now, if p is greater than 2q, that means that negative p over 2q, well, if the top number is bigger than the bottom number, you're going to have a number which is greater than negative 1. Now, that means we're trying to find solutions when we've got a line down here. Yeah, greater than negative 1. I suppose we should say less than negative 1, really. So it's going to be lower than negative 1. There are no solutions there. So when p is greater than 2q, we don't get any solutions. So I'll just put no solutions. Yeah, no solutions. Okay, we'll come back to that in a minute. What if p is equal to 2q? Okay, what that means is that negative p over 2q, well, if the top equals the bottom, you're just going to get negative 1. So let's have a look how many solutions we get for negative 1. All right, we get a solution here, and that solution is at pi. So I'll just write that down. the solution we get is going to be theta equals pi. The last option is if P is less than 2q, or negative P is less than 2q. Oh no, P is less than 2q, which means that negative P over 2q, that will be less than -1. Now what I mean by less than -1, I'm going to have some sort of negative fraction. And if I get a negative fraction, what I'm going to have is basically a line that goes like this. So can you see this one has two solutions? So I'm just going to write down two solutions. So now we can put this all together. We've already got two solutions here. Okay, so we've already got two solutions. Let's now summarize what we've got. So we've already got two solutions. So when P is greater than 2q, I don't get any solutions from cos. There are only two solutions. Now if there's only two solutions, that means there's only two of these tangents, these perpendicular tangents. So if there's only two solutions, two tangents, it basically means that the graph is concave. Oh, sorry, convex. That's the first diagram. If P is equal to 2q, okay, now I do get a solution, but I get a solution of pi, which is basically one of the solutions I've got already from sine. So there's still only two solutions. And if there's still only two solutions, the graph is still convex. We've only got two of these tangents. Whereas if P is less than 2q, I do get two solutions. Those two solutions are not 0 or pi. You can see them on the diagram here. The two solutions are here and here. So what that means is I've now got two more solutions. So I actually get four solutions, which means the graph has a dimple, the second diagram. Okay, so that proves it basically, and that proves the statement. So we've got for the first two, so this is where P is greater than or equal to 2q. Two solutions, it's convex as we've been asked, and when P is less than 2q, there are four solutions, so it has a dimple. So this is our proof here. Okay, but it's really sort of depends on an understanding of what a convex graph is and its tangents, and a graph with a dimple and its tangents. Right, you should now be able to do exercise 5D on pages 115 to 116. So as a quick recap, we have dx d theta equals 0. These are going to be tangents which are perpendicular to the initial line. So tangents, well, they're basically tangents that go this way rather than writing out perpendicular to the initial line. Okay, and dy d theta equals 0. These are going to be tangents which are parallel to the initial line. And just remember that depending on the graph, so a graph like this, for example, only has two of these, yeah, and a graph that has a dimple, there we go, so a lovely dimple there, it has 1, 2, 3, 4 of these. Now that's the same if the graph was facing the other way. We could have a graph where it's actually the dimples at the top, like that. That's possible. And yeah, we can do the same thing again about like the number of tangents here. Yeah, 4 of these dy d theta equals 0 tangents if it's got a dimple that way. Yeah, so that's something else we can use to help us try and prove whether something's got a dimple or not.